Okay, so today we'll talk about wavelet transform and mainly, yes. So it's really the very foundational, the very basic multi-resolution decomposition of images. And we look at the basic Haar wavelet and the Hadamard wavelet, and then the Walsh-Hadamard wavelet. So why wavelets? And if you look at this uncertainty principle, the Heisman uncertainty principle, what we have, if the x-axis is the position of a certain particle and the y-axis is the speed of that particle, then if you are really certain in a certain index of certain axis, which is in this case the position, if you are certain of the position, then you are really uncertain or very highly uncertain in the speed, and vice versa. If you are very certain in the speed, then you are really highly uncertain in the position. And that's basically the idea about this decomposition and the multi-resolution analysis of images. What we have the spatial and we have the frequency. And if you have very, very small window in the spatial, then how does that look in the frequency and vice versa. And that's basically the idea. And we mentioned before, when we talked about the image quality assessment, the human vision system, that this decomposition, it's necessary to mimic certain features in the human vision system. There are tons of different ways how you tile your frequency content, your frequency plane. The one on the left here is just a uniform tiling in the time frequency space. And the one on the right-hand side is the wavelet based, where you have a different, is non-uniform. And then there are other ways, and I mentioned this before that maybe we have time. It seems it's getting very tight to talk about directional transform. Directional transform, these are things like curvelets, sizelet. These are transform where they really capture the tiling itself is to capture certain specific directionality features in the images in the direction. I'll see if I can have some demo at least maybe next week about directional transform, but we're not going to get into the details of those. So I have really few, if you look at the PDF before the lecture, we have few toy examples to really illustrate this, especially for those who have never seen multi-resolution approximation before this course. So imagine that you have this sequence, and we have the units are 1, 3, or the magnitude of these samples are 1, 3, 2, 4, -1, 5, 7, and 9. And now I want to really have 2-by-1 approximation. So I have two operations. The first one is the sum. The second one is the difference, right? So, and now the dimensionality in this is 2. So I take the first 2. The sum is 4. The difference is 2. 3 minus 1 is 2. I move the window to the next two samples. The two samples are 2 and 4. The sum is number 6 in here, and the difference number 2 in here. And I keep doing that. So I end up with this first level approximation where I am representing these 4 samples using these 2 sequences. Each one of them is of length 4. The first one is the sum approximation, and the second one is the difference approximation. And if I keep doing the same operation at every single level, so now I go to the next level, and now I look at the sum that resulted from the first level of decomposition, and I do the same operation. I have a sum and a difference. Now I take every 2, so these 2 samples in here, 10, the second 2 samples will give me 20, and the difference between the first 2 samples is 6 minus 4, that's 2, and the difference between the third and the fourth samples of the sum is 16 minus 4, that's 12. So now I have a second level. So this is level 1, This is level 2, where I have an approximation of this sequence of 8 samples. I'm approximating it with these 2 samples in the sum and these 2 detail or difference in the detail sequence. I can go one more time because I can take the sum of 10 and 20, I get 30. The difference is 10. Right? So now I have level 3. Right? So I cannot go any further because I'm now have only a single sample in the sum. So now let's look at this overall. So here's what we did. What we did is we have an approximation and a detail. I have this sequence of 8 samples. This is my signal. And then I approximated this sequence. I can tell you that I can approximate it within the sum, which is 30. Right? So I start with 30. And then now I can add a detail. So now the first detail is 10. These together will produce to me this approximation, right? So now I can approximate this 8 link sequence using the numbers approximation 30 and 10, which will give me 10 and 20, right? Of course, there is a loss in terms of resolution, right? It's an approximation after all. Or maybe I can now, I say, I want to add more detail. So I add the detail. So I have the approximation, the sum. I add the first level of detail. I add the second level of detail. If I do that, then I have this approximation of the 8 link sequence. Or I can add, on top of all of these, I can add this detail or this difference. So now I have this approximation here. I added to it this one, I added to it this one, and now I want to add this. And if I add this in here with what I have in here, then I get the entire sequence back as it is with the same original resolution or detail. So this just to give you an idea about what we mean by a multi-resolution approximation in this case. And you can see in here what we are really looking for is to have this kind of an approximation where as I decode more and more coefficients or more bits, then I'm adding to the resolution, I'm adding to the detail, right? And you can imagine we will be doing this in image coding next, where if I'm streaming to a receiver in a very, very intuitive way, I could start by saying for my entire image or for an 8x8 block or 16x16 block, what I will start with is the DC value, the average of that image or the average of the block. And then as time passes by, I will add more detail. So you can see basically I'm adding what these details are what. I'm starting with the DC, the average. I'm adding low frequency, higher frequency, high frequency, and so on. So basically, and you have experienced this in the past. This used to be very common. I'm not really sure nowadays with the high bandwidth everybody has, but when you have really a very high resolution and large dimensionality image, when it comes through on the web browser, you start to see 2 different versions, and we'll talk about those when we talk about JPEG later on. But one of them is you have the entire image there. There are some values there, but there's really very, very blurry, and it's almost like very, very washed out. There's not much of a detail, and with time, within half a second, 1 second, depends on the bandwidth, you start to see more and more detail, and then within 2 seconds, you have the entire image very clearly. So that's basically it's a very important scalability in streaming concept, and that's why the wavelet actually we can do the same thing in DCT, and we'll talk about how JPEG is doing it, how MPEG is doing it. But at the same time, we look at the JPEG 2000 standard, which is really the most common one for images nowadays on the internet. and they are using the wavelets because of this approximation, where you have this streaming basically built into the coding itself. Yeah, so the position, this question about the location and the position of these pixels. And that's basically have to follow a certain predefined protocol. So we had the zigzag, we mentioned that last time. We have a zigzag as approximate, that's kind of the most common one for images. So in your data structure, you have to have that kind of protocol in place about how do you trace the pixels within your block or your image. But we'll talk more about those protocols when we talk about the standard JPEG and MPEG later on. So in here, if I'm streaming this, for example, then I'm showing this one first, and then I'm showing this with 10, and then I'm showing this detail next, and then I'm showing or displaying this one here, right? So this is basically kind of a serial approximation of the signal in here. And we'll talk more about, is this really, in terms of compression ratio, is this a good compression ratio compared to when you do it at once, like apply just a DCT for the entire sequence. And we'll talk about those trade-offs. Having this approximation and details give you this capability to have multicasting, meaning that for some it's the same cache server for the same content server with a certain movies from Netflix, for example, and then you send the same movie to user A with only approximation and detail 1. Another user, you send approximation detail 1, detail 2, and 3. So you have this kind of quality of service built into the code itself. And we'll talk more about these in more detail. We'll talk about JPEG and MPEG, and which will be the next topic. So let's look at in the 2D case and look at this as another toy example in here. And imagine that I have an image on the left-hand side, and I have these pixels A, B, C, and D, and I want to create this multi-resolution or a wavelet kind of like transform of this image. And again, this is just a toy example. So what I will be in my transform, I'm defining in here in this toy example, a toy transform, if you like. What I will be doing, my approximation is the average of these pixels, and then I keep the other pixel values as is, right? Right. So now, what's happening here? This block in here is my approximation. Just to have some analogy between this example and the 8 sample sequence that we had in the slides before. And then this corner here, we had a detail, another detail in this corner, and another detail in this corner. Okay, so in this toy transform or wavelet-like transform, my approximation is just the average of the pixels, and then the details, and over there I had a difference as the detail. In here I just chose to have the detail as the same pixel values as they are. So now let's apply this kind of toy transform to an 8x8 image. So let's start with this. So I have an 8x8 image on the left-hand side, right? And I'm looking at applying the first level. I'm looking at the 2x2 blocks of the image, and they are color coded in here, so you can really trace what's happening. And this is really the credit goes to some of the students who created the animation. So the first pixel is 1, and then 1, 5, and 9. And then I want to replace the approximation of this 2x2 block, right? I'm representing this 2x2 block using the average. It's 4 in this case. And then the other 3 detailed pixel values, they go as they are. So 1, 5, and 9. I'm not doing anything different. I keep doing that for every 2 by 2, right? So I'm replacing the next 2 by 2 block with the average, which is 4 in this case. And then the other pixels values as they are the detail. I keep doing that for every 2 by 2. I keep doing the same process all along. So now in here, what we have the first level of decomposition, where I have the first level of approximation. This 4 by 4 is an approximation of the image on the left-hand side. Why? Because every number in here, in this approximation, is the average of 4 pixels in the original image, right? And those pixels are, you can see in here, basically we have the blue, right? We're replacing these with the average. And then the orange, the green, and the yellow, they are the detail. So now, what I have in here, yes, on the left-hand side, I have an 8 by 8 image. On the right-hand side, I have an 8 by 8 decomposition. So where is the saving? The saving is happening because the first 4 by 4 are really the approximation, is the average, right? The approximation. And then the other ones are the detail. So now in this wavelet-like toy transform, if I have the approximation alone, then that's the average of every 2 by 2, then I can display that image as an approximation of the one on the right-hand side. However, if I can afford more bandwidth, I afford more time to decode, then if I can get the details, I can get all of them. If I can get all of them, then I can easily transform back to the original image. I can display it at high resolution. If I have only one of them, then I can have some way of a detail in a certain direction. And that's the idea. Usually, what we have is, this is really the approximation, the first level, with all the details all together. So level by level means every level has its own approximation and its own all detail. And then you jump to the next. You don't really create detail within the detail. So it's not really practical to say, I will send only this detail, but not these ones. It's not really, it doesn't work that way. How it works, I have a whole level of decomposition, which is what I have in this case, either approximation or approximation with all the 3 details in here. Now, the next level, what I will do is the following. What I will do next is I will go to this approximation, exactly what we did in the 8 length sequence at the very beginning. I take this approximation here and I apply a decomposition on top of it. So now I look at every 2 by 2, right? And then I take the average. The next 2 by 2, take the average. The next 2 by 2, take the average. And the next 2 by 2, take the average. And then this detail 4, 5, 3, they are here 4, 5, 3. This one is a 2, 5, and 3, 2, 5, and where's my, sorry, 2, 5, and 3. It's the orange one. And then I have 5, 4, and 6 in the green. I have 5, 4, and 6 in the green. And then I have 1, 5, and 2 in the yellow, 1, 5, 2. These are the details. So now I can replace this whole approximation from level 1 with this approximation from the second level. And now I get this. You see now? So now what do we have? We have this second level decomposition of our original image, where now I have this is as approximation, right? So this approximation here is roughly, it is really the average of every 4 by 4 pixels. So now I have this 2 by 2 image as my approximation. I can add to it this level of detail, which are in the orange in here, the green here, and the yellow in here. If I add these, then what I will be getting is basically the first level decomposition. If I add to it these details in here, then I get the original image back. Yeah, this is just a toy example. So the averaging in here, this is just a toy example. It's This is just an illustration of what decomposition mean, different levels, just to kind of motivate why we need this multi-resolution decomposition and how we can obtain it. This is totally a toy example, and that's why I call it a wavelet-like transform. You can think of this as a toy transform. And then now, can I still do more decomposition? Since I have this is 2 by 2 approximation, then the answer yes, I can do one more. So I take that 2 by 2 approximation. I do the same procedure as before, right? In here, and then this is basically becomes our approximation, our decomposition in this case. And this decomposition here is very straightforward. Is replacing it with the same values. Why? Because 4 will average. I have 1 pixel. The value is 4. The average is 4, right? So now, and these are the pixel details. So now this level in here is the third level of decomposition. This in here overall is the third level of decomposition. And then this one here is the third level of decomposition, right? So now, if I'm streaming this, what are the numbers I'm sending to the decoder? I'm sending 4 first. Next, I'm sending a packet that has 2.7, 3.7, 5.5. Next, I'm sending all those numbers 4, 2, 3, 5, which are the ones I have here, here, and here all together. 5, 3, 1, 2, 5, 5, 5, 6, 4. The next ones that I'm sending all these numbers in here, the 16 of them, 16 of this number, 16 of this number. So so this is the second level. Then the third level is the 16 times 3 numbers, right? So I don't really resend again the 4, right? Because if I have, this is my bit stream, and then I am a device. I have very small resolution on my display. I don't really need to decipher the entire image. Then it's enough for me it's enough for me to take this level and I say, okay, I'm done with this image. Maybe somebody else has a better device, has a bigger screen, will say I will take this and this. So now I have this, I have more capability. Or somebody has really very powerful display. We can take the entire thing, right? So, okay, so that's the question I was referring to. So usually it's level. So if you are here, let me see if I can take this highlighting. Okay, I can't. So if I am in this level here, right? You don't pick and choose between these different details, right? Unless you want to have some kind of predefined, but within you take it level by level. So usually I have one packet that has this approximation. A second packet has the first level of detail. You see these numbers? The fourth packet will have the next level of detail, and the fifth packet will have this detail. And now if it's a multicasting protocol, for example, on the streaming, then I will just take packet 1 and packet 2, I'm done. Or I want to take packet 1, 2, 3, and sorry, this is 3. Why? I don't know where this 4 came from. This is 3, and this is 4. Okay, this is 3. This is 4. Or I take the entire thing, right? You don't really divide within each level in there. And from a practical point of view, when you are decoding, you want to make sure basically you are really in sync in terms of the bit stream. You know what you are on the right bits. Otherwise, you'll be out of sync. Then you have to wait for the next. We'll talk about those details more. But within each level, you don't really split. Okay. So now this our okay. This is our toy transform took this image in here, produced this approximation. We have one approximation, which is number 4, and then we have 3 levels of detail after that. So we have 3 layers of decomposition happening. And as you decompose more and more of these levels, then you're adding more and more detail to the image. And here is just an illustration, a real image, the tiger one. So if you do the first level, this is the one on the left-hand side. This is the second level. You see, basically, this is the approximation, and the other ones are just the detail. And there's one more, I think. Yes, here. And then, given the image size is 1000 by 1000 or 1024 by 1024 pixels, is a 1K image. Then we can, it's one megapixel basically image. Then we can have 10 levels of decomposition, right? And then if you do that, you cannot really see it clearly, but it's all the way you can see the decomposition 10 levels over there. And now what you stream, you start streaming the first one here, and then this is the next detail, next detail, next detail, next detail, next detail, and then finally the final detail. Right? And that basically helps quite a bit in the streaming in here. And just to kind of give you a hint of what's really happening, imagine you're transmitting a video, and then you have 30 frames per second, meaning that you want to send, the video is high definition, you want to send basically every 30 frames within 1 second, right? So you want to make sure that they are really received. So of course there are much more complication within what we do in the coding, but just remember that that's what we are trying to do. So the question that you have is, if every frame is one packet on the internet, and then there's some kind of congestion in the network, and now the question is, do you sacrifice and drop that whole packet, or because it can get lost at a certain server in between or a router in between, and the sender and the receiver? And so that's one scenario, you drop it, or you say, my first packet has the approximation, right, that we have in here, and then the next packet basically has the next detail and the next detail. So now, if congestion really happens, I want to make sure at least my display, my user, my client can see an approximation of the image, although it's not really the highest quality. So I rather do this strategy over sending the entire, basically kind of without having any multi-resolution or decomposition of the image, just into kind of a 1 or 2 packets as rigid. So you have these 2 strategies. The first one is the scalability, right? Because you have this approximation and detail. And the second one, you have kind of a rigid representation of the image. And that's why it really feeds into this whole rate distortion calculation that we talked about. But I just want to give you intuition of why this becomes important within the image coding, image streaming, and video coding and video streaming scenarios. And then, of course, if you do this toy transform, you can go back and inverse transform this, so you can really go backward, which is very important. So you can really recover your image from the transform. And here is basically the calculations. I will not really get into those slides. You have very self-explanatory. And then you do the same thing. You get your image back from these approximation and a 3 level of decomposition that we have. Okay, so now the first basic wavelet transform is called the Haar transform, right? And you can see now, after I had my toy example, which we just average and have B, C, and D as they are, the Haar transform has specific calculations. So The same thing on the left-hand side. We have pixels A, B, C, and D. And then in here, I replace the first approximation with an average. And the next one, I have A minus B plus C minus D, and then I average over 4. And then the next one is A plus B minus C minus D. And then the fourth one is A minus B minus C plus D. Okay? So I have some labels in here. This is LL, meaning basically is low. This approximation here is low in both directions, meaning low frequency in both directions. And here I'm looking low in one direction and high in other direction. This one is high in one direction and low in other direction. And then here is high in both directions with frequency content. And you can see from I'm adding A plus B and then minus C minus D. So I'm looking at the difference between the sum of A and B minus the sum of C and D. So this one here, right? So you can see basically I'm looking at, if I'm moving vertically, I'm looking about the change in intensity as I am moving vertically. On the other hand, this one here is A plus C minus B plus D. So I'm looking at the transition in the intensity as I'm going horizontally, as I'm moving horizontally. And this one is I'm looking in both directions. So I'm looking at A plus D minus C plus B. So I'm looking at that. So that basically kind of one way to look at how why we label these as LL, LH, HL, and HH. So if I apply to the same image that we had before, and now I have a new set of rules, because before, remember, before I had, in my two example, I had 1, 5, and 9 transition SDR, but now we have calculations to capture horizontal, vertical, or in both direction kind of frequencies. So these are the calculations. The first one is average, as we had before. And then this is the second detail, the third detail, and the fourth detail as well. And the same procedure as before. I keep repeating the same procedure to populate all of these in here. And you can do the same procedure basically to 3 levels. In this case, it was an 8x8. We can do 3 levels of decomposition. And if you do that for this, the grayscale of this tiger image, and you can see basically in here, in the first level of decomposition, this is definitely is an approximation. It's an average. It's a blurry, and you can see in here, you see there is some tiny detail about the frequency, the edges, in the LH1, and 1 in here just to reflect. This is really our first level of decomposition. You can see in here the HL1. You can see some you can compare this one here. Oops. Yes, look at this, and look at this whisker, and this one here, it's nothing showing up here, right? So you can see HL1 as I'm moving, as if I'm walking vertically, I'm looking at what kind of frequency that I'm getting here. This one here, I'm moving horizontally, and since this is a really straight line, the whisker, there is no transition basically as I'm going that direction. And then here, you cannot really see much. There is some here, but nothing happening here. So you can see basically what we mean by LH1, HL1, and HHN in this case. What kind of frequency could we really doing? And then the next thing is I take this one here, another level of Haar transform. I get this approximation of it. And you can see now I have kind of a multi-level, a multi-resolution approximation of our image. So this has become the LL2 is size-wise is 1/4 of the original image, and then I have this approximation here, this one here, this one here, this one here. So one thing that you have to keep in mind is that if I don't have LH2, or HH2 or HL2, then I cannot really calculate LH1, HH1, and HL1. There is that dependency, right? That's happening in here. So that's basically something you can think of. If I'm transmitting this into different packets, if the packet carrying these details in here are lost, then basically, even if I receive these packets, I cannot really decode. So later on we'll talk about some strategies, but we'll not really talk too much about what kind of streaming technology we have in the internet to avoid such problem. So if we keep doing that 10 times, because we have 1024 by 1024, it's really difficult to show all the levels, but here is basically 4, 5, 6, 7, 8, 9, and 10 is somewhere there. But you can see that's basically the Haar for this. So the Haar, the best way is to look at it in the 1D case. And you can see in here, we look at T between 0 and 1. And there are only 4 of them. So there are 4. So the first one is all ones. The next one is 1 and -1. The next one is 2, -2, and then 0. And then the other one, I have 2 in here, -2 and 0. And now the question is, what if I have a sequence of dimension 4 in the 1D or 8? You just multiply this. You scale T, you scale this by 8, for example, for our 8 sequence, right? So you can see if you have from 0 to 8 for our 8 linked sequence, then this is all 1. That means what? I'm looking at the average of the entire sequence, right? And the next one, the next level of detail, I'm taking the average of the first half, right? And then subtracting from it the average of the second half. And then the next one, the next detail, there are 4 detail in this case. The next detail is I'm looking at the first 2 and in our 8 linked sequence, and then I'm subtracting from it the average of the next 2, and then I'm not really accounting for the other half. This one is the other way around. I'm looking at the other half. I'm looking at the first 2 and the last 2, and I'm not accounting for the first half. So this is just one way to look at how Haar transform is operating in the 1D case. We will have enough examples today to really get you in understanding this. So the best way I want to really look at this, the ESP6250, you'll get in much more detail about this, and I think the foundation in machine learning can cover some of this material. So I really want to go ahead to the 2D case. So these are the basis functions. So if I have a 2-dimensional Haar transform, here is basically the basis functions. The first one is the average, right? 1 for everything. The next one, I'm looking at the frequencies basically as if I'm moving horizontally. I'm looking at transition intensity values, and vice versa for this detail. And this detail, I'm looking at transition in both horizontal and vertical. That's where you have 1 and 1 diagonal, and then -1. Look at the example that we had before when we had A, B, C, and D, right? And then in one case, I said I'm looking at A minus C and D. The next time, I'm looking at A, C minus B, D. The next one, I'm looking at A, D minus C, B, right? So these are the 3 different details that we are looking at in the Haar. So now if I look, so this one basis, this is 2 by 2 basis, right? This is for a 2 by 2. The next one is 4 by 4, right? Basis, and here is how it looks like. So imagine it's I have 4 by 4 pixel. If I take an image, I divide it as, so far in our examples in this lecture, we stick to 2 by 2. Imagine that we're going to go now to 4 by 4 because 4 by 4, 2 by 2 for high definition images is really very small, not enough detail there. So most likely there is not much frequency changes in 2 by 2 in a high definition. So we like to go to 4 by 4, 8 by 8, 16 by 16. So here is the 4 by 4, and the plus white means is +1, and the negative black means -1. So you can see basically this is what we are looking at. And I thought I had 8 by 8, but maybe later in the slide we'll talk about those. So now, what do you notice in here? Is there you cannot see my writing? Yeah, I think I still see it because I am connected through two different accounts. So definitely from the other computer I can see my writing. So maybe there's something at your end. Okay. Thank you. So in here you can see what do you notice in here? You see what at each level of detail, what are we looking at? So in here we are looking at the entire basically 4x4. In here we're looking at the entire 4x4, 4x4, 4x4. But as you go to the detail, right? This one here, as an example, this detail, it's so localized. It's only looking at this part, right? It's zooming in, just specializing in a very specific part on the image. And that's basically what the detail is. So the details in the Haar transform are inherently really localized, right? So the same thing in here. It's very localized. Go to the next level and look in here. They are really very localized. This is localized. So each one of them, as if you took really your magnifier and just looking at the detail in a very specific location in our image. And we look at some examples to really illustrate this very important concept in here later on. So let's look at this calculations. When I implement this, and I have an image X. That image can be 2x2, can be 4x4, can be 8x8. Then I can transform it into Haar coefficient into the Y using this equation, which is 1 over 2 to the power 2n. And then we have this matrix. We'll define it in a minute. H sub n, I have my data or my image X, and then I have H sub n transpose. And I can obtain my X back using this inverse transform, which is basically I multiply with H transpose from the left and H n from the right, and I get this one. So now what are this? The first one is what is n? The second question, what is Hn? So n is, if we are assuming that our image is square of size 2 to the n by 2 to the n, then basically that's our n, right? So if you have 1024 by 1024 image, then n is 10, right? So now that basically you can really have a decomposition of 10 levels in this case. Now what is H? Let's look at this. So the definition of H sub n, it's iterative. So I can calculate H sub n from H n minus 1, right, using this matrix in here. There are two things here. H1 for Haar transform, as we define it at the first level, Haar transform is 1, 1, and 1, negative 1. And then I have this, what we call it, the canonical product, right? This canonical product. And I have this example on the right-hand side to illustrate that. So if I have these two matrices as an example, 1, 3, 2, 4, I want to really do a canonical product with this matrix 0, 6, 5, 7. Then basically what I will do, I'll take 1 from the first matrix and then multiply it with this second matrix as it is. Take the second element 2, multiply it with the second matrix as it is. Take the third element 3, multiply it, and so on. And then once I do that, then this will be the result of this special product in here, right? So now, if I'm going to calculate, imagine that if I'm having 2 by 2 as my Haar transform, then I'm done with H1. Now, if I have 4 by 4, then my H has to be a 4 by 4. So I need to calculate this H2, right? The second basis function in this case. So if I plug in here, n is equal to a 2, then I have to have H1 product with 1 and 1, and then a square root of 2 to the n minus 1. N is 2. That means square root of 2. The identity matrix 2, which is 1, 0, 0, 1, and then a canonical product with 1, negative 1. So if you do that, what we will have is H2 is our H1 is 1, 1, 1, negative 1. Sorry. Product with 1 and 1. And then I have square root of 2. I have 1, 0, 0, 1. Turn product with 1 and negative 1. Right? So that means I have 1 times 1 and 1. The next one is 1 times 1 and 1. The next one is 1 times 1 and 1. Negative 1, 1 and 1. And then I have the second row in here, square root of 2 times 1 and negative 1. And then 0 times 1 and negative 1. And then 0, 1 and negative 1. And then square root of 2, 1 and negative 1. Right? And this should give you this answer in here, right? So this should be 1 and 1, 1 and 1, 1, 1, negative 1, negative 1, square root of 2, negative square root of 2, 0, 0, 0, 0, and then the square root of 2, negative square root of 2. Yeah, I think it's correct. Yes, it's the same. Yes. And now, once you have H2, then the next one is H4, H3, and H4. So you can really do the same procedure and so on using this generalized formula in here. So this is basically how you can really find the Haar matrix. So you can really do the transform for your image based on how much levels of decomposition that you are trying to do in this case. The first one is 2 by 2. You can get H1 for that. The next one is 4 by 4. You can get H2 for that, and so on. So here is an example of an image, 2 by 2 image. And if you apply just a one level of transform, Haar transform, then we have 1 over 4 H1 X H1 transpose. And this becomes our Haar transform, which, but now you know that how to read this. So actually this is the lecture where from now on we look at the image where the upper left corner is the 0, 0, by the way. So this is really where we start to look at images as we do in MATLAB and in Python. So if by looking at this Haar transform, by the way, by now you know that this is our approximation, and these are negative 0.5, 0, and negative 1 are the detail in this case. How do I get this back? I use the basis functions. The 2.5, I multiply it with this, 2 by 2. And in the next level, the negative 0.5, this is the basis function it represents. And the negative 1 is a magnitude that represents this basis function. And the 0 is has this. If I do the multiplication addition, I get my image back 1, 3, 2, 4. So I'm hoping this is another way to look at the basis function in our decomposition examples. So now I'm going to go to another example where you can do this by hand, but there is a twist to it. So imagine that this is my 4 by 4 image, and now I really want to apply Haar transform. So I want to look at this as a 4 by 4. So I use the H2, and if I do that, here is my coefficient, right? So now, what we know that this is our approximation, right? But you can see in here, all these detail, there is not really much happening in the image. But for this high frequency in here, there is this detail in the image, right? So now, what we'll do next is to say the following. Let us do the following. Let's really take our Y, which is this one here, and as it is, the only change I will do is to go to this. I want to go to this coefficient here. I want to make this a 0, so that I have an error, or as one of you asked the question in the chat, which is, what happens if I really don't add part of a detail? Remember, we have this in here as a detail, right? So what if just one number, the negative one here, this one here, is becomes a 0? So what happens if that's the case? So if that's the case, then I will have, you see, this became a 0 in here, and then I will just call this as a y tilde, an approximation of y, or basically an error version of y. And then I want to apply this equation from previous slides to calculate what that x should look like. And here is the x, right? And here is the original x. So this is x tilde and this is x. So you can see in here what really happened. I have only one number that was -1 in the Haar transform domain that became a 0. That error in the Haar domain, it propagated to where? So if I compare this x tilde and this x, what do I see? So if I look at this, they are identical, right? If I look at this part of the image, they are identical. If I look at this part of the image, they are identical. However, this part of the image, right? What's happening here? Right? This is different. The limit was 0, 1, 1, 0. Now is 0.5, 0.5, 0.5, 0.5. So now what's happening in here is that if I have an error in a certain detail in the Haar transform, the propagation of the error is localized. Remember when I showed you the basis function, and I showed you basically at certain levels, plus and minus, they are so localized as if you are zooming into certain parts of the image. This is exactly what it is. This is just to show you that's the case, and you can do an experiment. And there's a question in the homework about this, where if I do this, what kind of an error in the image that I get back will I see? So in this case, it's localized. So localized, meaning that it's the impact of this coefficient being an error, it's limited to a certain local region in the image. It does not propagate to the entire image. And so that's really kind of a feature in this case in here. So here is the original image. This is from Petro and Petro book, textbook. This is the original image. As you can see, it has certain structure. And now if I have kind of reconstruct the image using the Haar transform 8 levels, then I have this first one, next level, next, fourth, fifth, sixth, seventh, and eighth. And you can see we reconstruct the image, and every time we are really adding a certain detail. So you can see if you want to view this image and you stop here, then this basically this image in here is the approximation of the original image, and so on. If you do that to the tiger image, and we have a Haar coefficient, so we have an 8x8 Haar transform. And then for each one of these, we just say, I am interested only in just looking at the first 15 coefficient and all the other detail. So I was looking at one approximation and 15 detail. All the other details, I just want to get rid of. And here is the reconstructed image. If I do the same thing, but now I want to even have a lower bandwidth, and I'm only interested in only the first 6 coefficients, then here is the image. And you can see there's very, very slight change. Only if you look at the whisker area, you can see some discontinuity there. There's some slight differences here and here, but overall, the perceived quality is really is maintained to some extent. So you can see there is really a very graceful for natural images transition between different levels of the reconstruction. They are much more obvious in here because the image in here is much more constructed, is much more uniform in the geometry and the structure than a natural image. That's why it's very obvious, basically, as you go from one level to the next, the approximation changes. Okay, so that's basically another example of the Haar. And then there is another related transform, is the Hadamard and the Walsh-Hadamard transform. So the first one is really the Hadamard transform. And here is basically remember when we had that equation that calculate Hn from Hn minus 1, the Hadamard basically is only have this conical product without having the square root 2. And so basically your your 4x4 is become this one, although 2x2 is the same as the Haar, but 4x4, 8x8, and 16x16 keeps changing. So that's Hadamard as one, and then I will talk in a minute about it. But before I do that, I want to talk about Walsh-Hadamard. So the difference between Hadamard and the Walsh-Hadamard, at least for our discussion in this course, is that I take the Hadamard, right? That H2, this is exactly obtained using H1, a product with Hn minus 1, and this is Hn minus 1, which is 1, 1, 1, negative 1. And then what I do, I reorder the rows based on the number of sign changes. So the first row has 0 sign changes. The second row has 3 of them. I go from 1 to negative 1, negative 1 to 1, 1 to negative 1 again. The third row has only 1 sign change. The fourth row has 1 to negative 1, that's 1. And then the next one from here to here. So you have 2 sign changes. This makes sense? And then I reorder the rows based on these sign changes. So I take the first row, it has a 0 sign change. The next row should be the one with the 1 sign change, which is this row. And then the third one would be the 2 sign, which was the 4th row in the Hadamard matrix, and so on. So you can see now, if I plot this, this was the 4x4. You can imagine this is the basis function for the Hadamard. This is how it looks like in the Walsh-Hadamard transform. And I think we have, yes, here is how the Hadamard transform, like for H1, right? Remember, H1 was 1, 1, 1, negative 1. And the next one we had, H2 is this one here. So this is the H2. This is H3. This is H4, which is basically, this is 2x2. This is 4x4. This is 8x8. This is 16x16. This is 32x32, the H5. That is 2 to the 5 is 32. So you can see basically this is how the Hadamard looks like. If I take the same H1, H2, H3, H4, within each H, I reorder based on the sign, the number of sign changes in every row. Then this is how the Walsh-Hadamard look like. So I'm reordering things to really have the detail. There's a correspondence between the level of the detail and the number of frequency changes or changes in both direction, horizontal and vertical. So just only, yes, you sometimes you will have a tie. So in that case, and then it will not. It just use one. There are some actually slight differences which surely use, but for now we'll not worry about it in this. We'll just the tie. Just take the whatever showed up first in the Hadamard, just keep it as the first one in the Walsh-Hadamard matrix. And now, this is really the important part about this discussion for the Hadamard Walsh-Hadamard. So imagine that I have the same image as before, and now this is the Walsh-Hadamard reconstruction. So all what we are doing in the Walsh-Hadamard, we're using these basis functions, right? And this is the reconstruction of the Walsh-Hadamard. And I just want you to remember, these were the ones from the Haar transform. And the question is, what are the differences between the two reconstructions? Look at this, right? What are the differences? Can I zoom in? And maybe not. Okay. Maybe I can just hold it. So any suggestions, what are the differences between the two? What do you observe? At the end of the day, we got basically the same image at the 8th level. We reconstructed the image, right? The first two, similar. The last one, similar, right? But in between, there are big differences. Anybody wanna? Maybe not. So the first thing you should look at, if you look at this, let's look at this example here. You start to see basically, you start to take shape, right? Look in here. Really big part of the image, right, is starting to take shape, right? There is exactly. So thank you, Pratik. So the approximation is really spread throughout the image, while in the Haar is really localized. So you can look at that. So look at this part of the image. Look at that in this reconstruction. Look in here. Look in here. You start to see early on in the reconstruction levels quite a bit. If you look at the difference between this level and this level, the only difference is just this part in here and this part in here and this part, right? So it's very localized. As you add more detail, they are really localized to a very specific part of the image. If in the Walsh-Hadamard and the Hadamard in general, you can see it's very spread out. So if I redo my experiment, when I zeroed out one of the detail coefficients in the Haar transform, I look at the error is really localized. If I do the same thing in here, then what do you should expect? We should expect, what would you expect? We should expect that something will spread out. That means the error will be throughout the whole image, not only localized for a certain region. Even look at this in the last layer, reconstruction level, from here to here. You can see basically it's throughout the whole image, and then suddenly we get the image all back. So there is localized and there is basically global and spread out effect in the Walsh-Hadamard approximation. This becomes basically very obvious from here. So we have the basis function 8 by 8 for the DCT, for the Haar wavelet, again localized, and then we have the Walsh-Hadamard, and you can see now in the Walsh-Hadamard basically it's very resembling big resemblance between the Walsh-Hadamard and the DCT basis functions. The Walsh-Hadamard used to be really in the early days when we didn't really have powerful computation, because all what you have is just +1 and -1. It was very easy to calculate these without much computation power. But with time, basically, we moved on to wavelet like Haar and DCT because we can do those in real time very, very, very quickly with the FFT transform as well. So this is about it for the